Hi everyone, welcome back to statistics and data analysis. So last time we talked about descriptive statistics about data graphs and measurements for central tendency and variability. Here I want to continue to help you understand what are the major measurements that we may use to describe correlation. So because in the previous lecture we did not finish all the exercises about the previous materials, so today this will be for the next week this will be the only video. Okay, you only have one video, and then I hope in the next Monday we will be able to finish all the exercises and the R programming tutorials for all these materials. Then we will be at a very good starting point for our later study about statistical inference. Okay, so let me start. Here, the fact I want to talk about is how to measure the relationship between two variables. So suppose I go to a city and randomly select 12 houses and record their sizes and prices. Okay, so I will get two sequence of numbers or two sequence of measurements about the size of house 1, the price of house 1, the size of the house 2, and then the price of house 2, and so on and so on. So for these 12 numbers, I'm going to first try to visualize them. Okay, so the first thing I want to do is to draw a plot or a scatter plot to get some ideas or intuitions about their relationships. So for example, the first thing I want to do is to see where is the first house. Okay, it's around 75 and 315. So 75 is around here and the 315 is around here. So I see, oh, this is this point. Okay, this point is the first point. Or for the second one is around 59 and 229. So I'm going to depict a point here to represent the second house. By repeating this process, I'm going to create a scatter plot with 12 points. Okay, these 12 points comes from these 12 pairs of numbers. And then intuitively we get the first impression. It seems to us that when the room size, when the house size goes up, the price will also go up. Okay, somewhat intuitive, and for us it makes sense. The thing is that of course we know size is not the only factor that affect the price of a house. Okay, there may be other factors, for example, locations, how old the house is, or is there a good university or a good elementary school nearby, and so on. There are other factors. Here we only focus on the relationship between size and the price, or we may say we only focus on the partial sources of the factors of prices. Okay, but here I just want to start with this very simple example to show you that when we have a set of data, we want to find some impression about the basic relationship between one variable and another variable. Okay, sometimes we say this is an independent variable or source variable, and the other one is the dependent variable or response variable. We try to understand how this guy affects the other guy, and so on and so on. So we're going to talk about it in more details later in this semester. Up to here, just make sure that you have the ability to prepare a scatter plot and intuitively see there are some relationships. Okay, so graph is good, but we want some numbers to describe or to summarize the degree of correlation. Correlation is defined as linear relationship. We're going to see it. So Now I'm going to introduce some measurements about correlation. So the idea is the following. I want to understand when one variable goes up, for example, when size becomes larger, does the other variable tend to go up or go down? This is of course somewhat random. Okay, it's very rare for us to see two variables with a certain relationship, but we want to know the tendency. Okay, when one variable goes up, for example, when size becomes larger, does the price tend to go up or down? That's the question we want to ask. Numerically or mathematically, what we want to measure is here. Suppose our xi, okay, x is the price. Suppose xi is larger than the mean of the price, the mean of xi. Okay, suppose this is the case. Do we see the y variable to be above or below the mean of y? Okay, that's what we want to see. If I have a large x means larger than mean, and it will usually correspond to a large y, which is greater than the mean of y, then we think there is a positive correlation, right? When one variable goes up, the other one tends to goes up. Or when our x is large, but our y is small, then we say, oh, then we tend to have a negative correlation. So let me highlight the two means on the scatter plot to give you a more concrete idea here. Okay, for each point here, there is an x coordinate, the size. Okay, for the 12th number, I know how to calculate the mean, and it's here. For y prices is the same thing. And then immediately we can see for almost all the points, they are at the first quadrant or the third quadrant. Okay, that means when x is large, y tends to be large, and when x is small, y tends to be small. If you have a set of data where all those data points tend to locate at the second quadrant or the fourth quadrant, then that means just the opposite thing. When one variable is large, the other one tends to be small. Okay, so that's the other story. But here I have something that all the points are at the first quadrant and the third quadrant. Here we say there is a positive correlation. Okay, when one goes up, the other one goes up. Or if it's at the second and fourth, then we have a negative correlation. So we are very close to the definition of measurement for correlation. Here, mathematically we define something called covariance, which is defined like this. So what's this? For each point I ask whether xi minus mu x, or the mean of x, is positive. Suppose this is positive, then that means the x point is here, right? And then I ask whether yi is greater than mu y. If this is also positive, then I know xy is at the first quadrant. And then the product of them, positive times positive, I will get a positive number. At the same time, if both of them are negative, okay, here, then that means the product of them is also positive. So whenever I have a point here or here, I get a positive product. If all the points are either here or here, then all those products will be positive. And then the sum will also be positive. And then this particular covariance will just be positive. On the other hand, if I have some points here or here, for example, in the second quadrant, then x will be smaller than mu, but y is greater than mu, so I mean mu y. So this product will be negative. Similarly, if I have a point here, then the first term is positive, but the second term is negative. So whenever I have points at the first or the third quadrant, I get a positive term in the summation. But if I have points at the second or the fourth quadrant, then I have negative terms in my summation. So after I summing up all of them, I get a summary or an aggregate effect or an aggregate measurement for all these relationships. And then I do a simple average to get the covariance. In general, the very simple idea is just to measure whether when one is greater than the mean, does the other one also greater than the mean? And then we use this particular concept to define covariance. This is population covariance, and similarly we have sample covariance. If we have sample data, then I still do the same thing, but for the denominator I divide it by a -1. Okay, so this is very similar to the definition of variance and the standard deviation, right? So again, the reason I cannot tell you at this moment, but we will talk about it later in this semester. So let's work on it with our example. I have all these 12 numbers, right? So I can calculate for each number what is the deviation at the first dimension, xi minus x bar. X bar is the average of x variable. So for each x I can get this. For each y I can do the same thing. And then for product, for this particular example, all these products are positive. In general, you may have a data set where most of the products are positive, but some are negative. It doesn't matter, because what we really care about is the sum of all of them. I should say the average of all of them. Okay? As long as the aggregate effect is positive, then we say there is a positive correlation. And then that means when one goes up, the other one goes up. If the aggregate effect is negative, then we say when one goes up, the other one goes down. Okay? So in this example, the covariance of our house sizes and the prices is just around 617. This is the average of all these numbers. So now, the first thing we can make sure is there is a positive correlation, because this number is positive. If this number is negative, then we say it's a negative correlation. But if we want to ask me whether this is a large number or a small number, it seems that it's hard to explain, right? We don't know whether 600 is large or small. And definitely it depends on the variability of each variable. If for each variable they have a very large variability, then intuitively, when you look at the two variables, you will have a very large covariance. Why? If let's say x has a large variability, for example, a large variance, then each number of xi minus x bar will be large, right? Because each point is far from the mean. Or for y, if it's also the same thing, then y will be far from the mean. So if these numbers are always large, then you tend to have a large covariance. So this 600 may be large in this case, but may be small in other examples. So we need to find a way to normalize them. That's here. Okay? The idea is very simple. Whenever I have a covariance, I can divide the covariance by the standard deviation of each variable. Okay? These standard deviations, they measure how variable each variable is. And covariance measures the relationship, right? So if I divide the covariance by these standard deviations, I will be able to take away those auto variability of each variable. Auto variability means the variability inside each variable. So after I do this, I will get something we call correlation coefficient. There is a great property of correlation coefficients is that they will always be within -1 and 1, no matter it's a population or sample correlation coefficients. Okay, so this is a very good property because now we are able to say if this number is close to 1, we say it's highly positive correlated. The relationship is just strong. Or if the number is close to 0, then we can say the correlation is weak, or even there is no correlation. As with our example, you may try to verify that if we divide the covariance by the two standard deviations, then we get around 0.729. Okay, this is our correlation coefficient for our house example. In general, for different applications, you may have different standards, but in general, a rule of thumb is here. If our correlation coefficient is around 0 to 25, we say the correlation is weak. If it's around 1/4 to 1/2, we say it's moderately weak. Or if it is between 0.5 and 0.75, we say it's moderately strong. Or if it is above 3/4, then we say it's strong. So in our previous example, it's 0.729, we say it's moderately strong. Okay, so this is just one particular way for us to say it, but this is not the standard answer for measuring how strong the relationship is. Okay, so for different examples, the decision maker must have its own way to interpret the correlation coefficient. There is one last remark. Correlation coefficients only measure linear relationships. Okay, so you may have two variables. They have a very strong relationship, but that relationship is nonlinear. Okay, for example, you may have a scatter plot with point like this. Okay, you can immediately see there is a very strong relationship between these two variables. But if you try to measure its correlation, then it may be not so strong because we are trying to fit all these data points with a single line. Okay? If the line cannot perfectly estimate or perfectly fit these data points, then the correlation coefficient will be weak. Okay, so keep in mind, when we are looking at the correlation of two variables, we are measuring their linear relationships. If their relationship is nonlinear, then we need other more complicated methods. Okay, but linear relationship is definitely a starting point for we to do investigations. So correlation coefficient will be really useful in our daily lives about statistics and data analysis. Okay, that's all I want to say here. Thank you.